Hello and welcome. Today's event is part of AIAA's Aerospace Perspective Series webinars. We're pleased to bring these talks to our worldwide community, giving you a behind-the-scenes look at current projects that are shaping the future of aerospace. Today's webinar is being recorded. If you miss anything or want to suggest it to a friend, a recording will be sent to the email address you provided during the registration process. We will be taking questions from the audience. If there is an appropriate time during the presentation, your question may be asked of the speakers. Otherwise, we will do a Q&A at the end. Please use the Q&A feature on your Zoom console. And now, to kick things off for the webinar, please join me in welcoming Clay Mowry, AIAA CEO. Clay, over to you.
Thank you, Vicki, and hello, everyone, and thank you for joining us today. At AIAA, our members are in the business of accelerating aerospace innovation, and there's no greater challenge or opportunity ahead than achieving net zero aviation emissions by 2050. The path forward demands innovation, along with visionary design, powerful tools, and bold collaboration. And today's webinar spotlights one of AIAA's most forward-leaning corporate members, Flexcompute. Their groundbreaking platform, Flow360, is doing what legacy CFD tools cannot. It is delivering high-fidelity, GPU-native simulations at unprecedented speed and scale. And this is not incremental progress. It's a generational leap forward in how we model, test, and deliver sustainable aircraft. And I'm privileged to welcome today two exceptional minds at the forefront of this shift. Dr. Chi-Chi Wang is the co-founder of Flexcompute and a professor at the Massachusetts Institute of Technology, MIT. He's a pioneering next-generation computational scientist bringing methods that exascale power to unsteady aerodynamics and turbulence modeling. He's unlocking insights that were previously out of reach. Also welcoming today, Dr. John Vosburgh, who's the Chief Design Officer at JetZero and former Chief Aerodynamicist at Boeing's Phantom Works. John has shaped over 20 commercial aircraft, and his leadership is blending wing body and hydrogen power design, charting a course for cleaner, more efficient aviation in the future. Together, they'll explore how Flow360 is enabling faster, smarter, and greener design, and how strategic partnerships like this are reshaping what is possible. So let's get started. And John, we get started with you, please.
Thank you, Clay. Hello, for those of you that don't know me, I'm John Vosburgh. I've been in the industry for 45 years now, and I really just love what I do. For those of you that do know me, you know that about me. And I'd like to just kind of mention that the last 4 years I've been working at JetZero after retiring from Boeing after 40 years there. And JetZero, for those of you that don't know, we're a startup company. Mark Page founded the company in 2019, but we got moving in earnest about 4 years ago when I joined. And at the moment, we're looking at a product that is nominally a 250 passenger commercial jetliner that would have a range of about 5,000 nautical miles. I mention these stats just because an aircraft that has that kind of capacity and range captures about 85% of the revenue passenger miles that are being served today. But just as importantly, it captures 95% of the carbon emissions that aviation is putting out in the air. So we had, when Mark founded the company, we had one real simple one-line mission statement, and that was basically to develop the next generation sustainable jet with a path forward to zero carbon emission. Not net zero, but real zero. And so that's the liquid hydrogen version of the aircraft. So today we're building a Jet A, designing and building a Jet A aircraft but we're looking towards the future, 10 years or so into the future, and trying to figure out what we need to do with today's design to enable us to have a nice smooth path and transition to liquid hydrogen. At the moment, as fuel costs go, liquid hydrogen costs about 2.5, 3 times as much as Jet A on a per energy basis. But by the year 2050, it's going to be almost on par. And at the moment, liquid hydrogen is only generating, the capacity of liquid hydrogen only generates single-digit percentage of the capacity needed for commercial aviation. But by around 2040, 2050, it'll reach close to that 100%. So we want to be prepared to capture that and capitalize on it. So much for JetZero and BWB. I'm going to go ahead and introduce you to Chi-Chi Wang. I'd like Chi-Chi to introduce himself actually, but I do want to say, Chi-Chi, the reason why JetZero and Flexcompute are working together and collaborating on this project is because I've known you and much of your team, including Philippe Spillart, Mike Park. I have recently met Vera Yang. She is a ball of energy and enthusiastic, and we're really glad to know her. Thomas Fitzgibbons has also been tremendous help getting us kick-started using Flow 360 at JetZero. So without further ado, Chi-Chi, why don't you let us know a little bit about yourself?
Hello, everybody. So my name is Chi-Chi Wang. I have been in aeronautics and astronautics department, first at Stanford, then at MIT for the last 21 years. So when I was young, there was all kinds of science fiction novels that predicts by 2025, which is today, we are all owning flying cars, and the well-off between us would be taking vacations on the moon and on the Mars. But instead of that, we today had a lot of innovation, not in aerospace engineering, but in software. We had internet, we had the social media, and most recently, we had a booming AI. So that begs the question, why is aerospace innovation slower than software innovation? Well, based on my observation at Stanford and at MIT, one of the key reasons is that the best students even in aerospace engineering ended up working for Google, Facebook, and most recently going into AI. But then there is a more fundamental question. Why do the best students not go to aerospace engineering, but go to working on software? The reason I figured was that aerospace innovation is really challenging. It is very risky. I mean, a lot of very good people lost their lives testing flying innovative airplanes. Innovation costs a lot of money, and those working on hardware understand that innovation in aerospace industry just takes enormous amount of time. And the dream here at Flexcompute is really to deal with risk, cost, and time in aerospace engineering. And the dream is to make aerospace innovation as easy as software innovation. So here, I'm just going to be using the example of our collaboration with JetZero to illustrate what we are doing to try to make aerospace innovation as easy as software. So for example, like a lot of the innovation both has huge advantages, but also has risks to address. And what JetZero is doing, putting engine at the back of the fuselage, has enormous advantages, but also there are questions to be answered, especially of airframe engine interaction. So is the engine ingesting separated flows at high angle of attack? And when would that happen? And how about crosswind takeoff? What is going to be the interaction with the boundary layer at the back of the fuselage? So again, this highlights what we do at Flexcompute using the most innovative GPU technology is to de-risk innovation. And as a result, accelerate design iterations of the methods of dealing with potential risks of innovative designs. And as a result of these fast design iterations, optimize the cost efficiency towards net zero. We're at a unique position to reduce the carbon emission of the product you design yourself and during the design process of running the simulations. So let's first get into airframe engine interaction at high angle of attack. So this is something John Wasberg just had a phone conversation with me at one night, and we just figured, how about we run a fully unsteady simulation like this? Really, virtually inside our CFD simulation, test fly a 1/16 scale test vehicle as it pitches up, starting from a low angle of attack to high and higher angle of attack. So now you see that the flow separation actually starts from the trailing edge of the outboard wing, and as the airplane pitches up further, the separation moves towards the leading edge. And this is a way after stall, which happens at around the 14 to 15 degrees angle of attack before the separated flow gets massively ingested by the engine of this 1/16 scale test vehicle. So doing simulations like that really helps figuring out what are the risks of innovative designs like that, and get the solution ready before the full-scale vehicle actually shown any phenomenon that needs to be dealt with. And this work is done by Thomas, who is shown over here. And the same thing as the next work, which is the engine installation effect at crosswind takeoff condition. So this is another simulation done by Thomas of simulating how the engine operates when sitting on the ground, which means there is no forward speed of the engine, but there is wind, there is high crosswind coming from the side, and the engine operates at takeoff thrust conditions. What you see here is that there is a simulated back of the fuselage of the JetZero airplane beneath the engine. And because there is crosswind, the boundary layer, the vorticity in the boundary layer gets sucked into the engine. And this creates a very challenging phenomena for the fan face to deal with. This combined with the separation on the windward side of the nacelle inlet creates non-uniform total pressure at the fan face that needs to be endured or designed away by the engine. And we here have a more zoomed in view of what is happening. As you can see that there is still one strong vortex at the center. If you look very carefully at the purple vortex, it's a very strong vortex that gets sucked into the engine, and that vortex also dances around. Around these very strong vortices, there is also a system of weaker vortices that also gets swirled into the jet engine. And doing this kind of simulations helps us quantify exactly how big the potential problem is, and very quickly design our system away from any problem that might be helpful. And having a GPU-native simulation, sorry?
Chi-Chi, do you mind if I interject a couple things here?
Of course, go ahead.
Yes, so what we saw in the previous animation with the aircraft, that was our 1/16 scale low Reynolds number vehicle. The airfoil stack on that is nothing similar to what we're actually flying for the full-scale demonstrator. But we have this opportunity to look at the flow separation patterns, and we'll be using this model to test out vortex generator patterns as well as bordelons to figure out how to control our stall characteristics and post-stall characteristics. If we go back to the propulsion animation here. We knew that this was going to be an issue, so we started looking at this problem even before we started collaborating with Flexcompute. And but simulations like this show us the issue, and then we go and invent technology to go tame this issue, which we have done. We won't be showing that here today, but these are type of simulations that a lot of people in the industry don't realize that you have to do to get an airplane with some operational capability. And this is a very high crosswind condition at max sea level static thrust. And so this is kind of the worst case scenario. But having these simulations the way we do enables us to go figure out how we go solve the problem, and we've been successful with that. Thank you, Chi-Chi. Go ahead.
Yeah, thank you, John, for the further explanation. So this is really illustrating the dream here at Flexcompute, and this is to try to make aerospace innovation as easy as software innovation. And we are hoping the next few decades to be a aerospace boom and in general hardware boom, such as what we have experienced for the previous few decades of software innovation boom. And we are doing this through de-risking innovation, accelerating design iterations, and optimizing cost efficiency by providing you the best, fastest, and most cost-effective simulations, such as the ones we have been working with JetZero. And I will leave the rest of the time for discussions, please.
Chi-Chi, are you available to take a few questions at this point?
Yes, please.
Okay. There is one question here. Are the engines center line parallel to the aircraft center line or offset by a small angle?
I guess that would really be a question for me. And the engines that you're seeing in this 1/16 scale model are parallel, but that isn't to say that the real airplane will be. So.
Yeah, thank you, John.
Yep.
Certainly. These questions may not necessarily be in order, so I apologize for that. But one individual is asking max separated flow is. So it sounds as though they would like an explanation on max separated flow.
Max, I'm not sure what you're referring to.
Yeah, it's somewhat cryptic in the Q&A. So I would invite the individual that posted this to resubmit, and then we will attempt to answer that live for you. So thank you. The next question is your CFD GPU optimized code open source?
It is not.
Understood. Do you want to go into any explanation, Chi-Chi, on why you are keeping that closed? And is it related to trade secrets and that kind of thing, just to give a little context to your response?
Yeah, basically that allows us to provide the best service to our customers, such as JetZero.
Absolutely. Thank you. Next question is, we recently witnessed a commercial airline crash in a flat spin, uncontrolled descent. What characteristics of this blended wing design might promote this tendency?
Well, let's see. I don't want to speculate, but on what happened with the other incident, we have to certify this airplane just like we would certify any other conventional transonic transport. And So there are no rules change that we're requesting from the FAA. The regulations are the same. We will design and have to certify to those same regs. Our airplane, well, I will not put my name on an airplane that's not safe to fly. So we're working those issues. And I guess what I would also like to say is that we have these flying test beds so that we can go, like in this particular case, the separation here starts out at the wingtip and moves inward, whereas our full-scale high Reynolds number vehicle, flight Reynolds number vehicle, we've tailored the separation to start more inboard, just like we would on any other conventional wing. I really don't know much more to say on that, other than there's a bunch of us working here at JetZero that have many decades of experience, and we're very much aware of what we need to do to get this aircraft certified.
Absolutely, John. Thank you for that. We know that safety is process number one. Yes. Across the board, and we appreciate and know that you all are supporting that for the industry. Next,
I'd also want to add that a lot of the simulation and analysis, the de-risking Flexcompute helps our customers do is related to safety, right? So we have many other customers, for example, who is concerned about the landing and of their aircraft. That like what we do is we can actually in a simulation fly through an entire landing process and helps at various windy conditions, and that basically helps you de-risk what are potentially safety problems. Yeah, this helps innovation a lot.
Outstanding, thank you.
And I'll add one more thing to this, is that in any kind of aircraft development program, we have to collect tens of thousands of data points throughout the flight envelope. And at JetZero, we're leaning heavily on numerical methods. We will still have wind tunnel tests. In fact, we're going into our low-speed wind tunnel test in just a few weeks. Our high speed will be later next year, but with Flexcompute and GPU enabled, it allows us to go even in the early development stages of a product, run thousands of points. We don't necessarily need to run the 10,000 or more set of points for the full, for the final aircraft, but understanding where we need to study the problem in our early stages of design really helps us avoid having any of these surprises. We certainly don't want to be surprised when we get into flight tests. Nobody does. So it's what we're doing a little bit different here at JetZero is leaning real heavily on the numerical methods, the accuracy of the numerical methods, and the cost effectiveness of the numerical methods. And so that's why we partnered up and are collaborating with Flexcompute to bring that capability to the design environment here at JetZero.
Yeah, thank you.
Chi-Chi, did you have something else to support that?
Yeah, I was just trying to say, not only minimize the surprises you have in test flight, but also minimizing how much surprises you have in the wind tunnel test is also useful, because wind tunnel test is expensive. And if you minimize the surprises, it reduces how often you have to go back to a wind tunnel to have more complete data.
Okay. So Chi-Chi, we do have this list of questions that that we had worked on together. Shall I start with those and go ahead and work through those?
Sure.
Okay, for Chi-Chi, this is legacy CFD tools are slow. Sure, but is the industry really ready to abandon decades of entrenched infrastructure for GPU native tools like Flow 360?
Yeah, I think it's going to come sooner or later. So, I mean, we have been seeing a lot of CPU style CFD tools still being used a lot, but the time for GPU is coming. The CPU code is still being used most often because there are still capabilities we are missing in the GPU code, which we are rapidly closing. And also because people have large CPU clusters, they still takes time to build the GPU clusters. But both are working very rapidly in the direction towards our advantage. So what I see another issue rather than CPU, GPU is a cloud versus on-prem. And a lot of people are now starting to use the cloud more and more, but we realize there are still many companies, particularly many projects inside a lot of customers that they want to keep on-prem. So that is why we offer both a cloud solution, which you submit cases in the cloud, and they can be done in a very secure ITAR environment. Or we can deploy our solution, which actually replicates the cloud experience in the on-prem delivery. So now we're offering both.
Thank you. So John, a question for you. The blended wing body isn't new. It's been studied for decades. What's different this time? Is the CPU native CFD actually what's unlocking viability, or is that just a piece of the puzzle?
Well, it's certainly a piece of the puzzle. I mentioned earlier that we're leaning heavily on numerical methods to get the design right before we start testing it in the wind tunnel, and certainly before we get to first flight. But you know, fundamentally, that's not a lot different than what we've been doing during the course of my career. When I started in the early 80s, we certainly were leaning on wind tunnel experimental tests a lot more than we are today. Halfway through my career at Boeing and McDonnell Douglas, we started actually using the wind tunnel more as just a verification step that we got everything that we were expecting to get. And that process has been, you know, improving ever since. Having new architectures and new CFD capabilities and new algorithms and new turbulence models, all of this is combining together to make this. In fact, in a lot of cases, we get better results with the numerical methods, you know, studying the flight environment than what we can build up from a wind tunnel low Reynolds number. So it's the game has changed. It's taken decades to get to where we are. But you know, the question that you asked Chi-Chi is, are we in the industry ready to switch architecture and hardware and everything? Well, we've been doing that from the very start. When I first started, we were running on IBM mainframe and out-of-core flow solvers with full potential methods. We quickly adopted the vector processor capabilities of the Cray. Then we went on to parallel processing on Crays. Those were small-scale parallelisms, but the whole time we were developing the algorithms as well to map well to the computer architectures. You know, this is not a big deal for me anyway, to jump from the processor, the CPU architectures to the GPU. It's just another step in the process. So just thought I'd touch base on that question as well.
Yes, absolutely. So just another piece in the puzzle and the progress continues. John, JetZero is betting big on radical designs and sustainable propulsion. What's the single biggest risk that could derail the vision, and how are you hedging against this?
Well, entering this market is really, really tough. There is a large capital investment that has to be made to get us there. On the technical side, there are some risks associated with the BWB, and I'll say that they're less aerodynamic than they are structural. We're betting big on composite technologies and building off of the work that NASA and Boeing did on Perseus for the non-circular pressure vessels. We're taking that and going forward using that technology, but trying to improve it on our own. So that's one element. There's even for a well-established aircraft company, there's risk every time you launch a program and try to bring it to in-service operation. So there's just a number of things that can that we have to be on top of and stay ahead of.
It's not for the faint of heart, but you're willing to go the distance.
No, and I'll tell you, if you don't think you can do it, you won't. But at JetZero, we think we can, and we're going to do it.
That's so impressive.
Yep.
Absolutely. GT, over to you. So CFD is notorious for the garbage in, garbage out problem. With faster tools like Flow 360, how do you make sure your engines don't just make bad decisions faster?
Well, you can definitely make bad decisions using CFD. And what we are trying to do is, so first of all, make it much easier to make right decisions. So, for example, like if you look at what we are providing, right? We're providing a much faster and cheaper tool. So I just want to make an example of the flow separation example. So you don't just have to run one simulation. You actually have to run a series of simulations with different side slip angles and different thrust conditions of the engines to map out the entire boundary for which you have dirty flow going into the engine, right? So with the traditional CFD tools, you can only run a very limited set of scenarios, and you have to interpolate between them. With much better CFD tools like us, you can have much finer resolution in your alpha, beta, engine, operating condition matrix. And that removes the need to interpolate, and thus giving you a better decision-making tools. And also with higher fidelity simulations, you don't have to simplify your geometry that much and remove the risk, or at least reduce the risk of getting wrong answers due to having to simplify the geometry, having to run with a coarser mesh than what you ideally need to. And also we are removing a lot of the considerations that has to go into traditional CFD tools. For example, we make mesh refinement studies much easier, much faster than what you can do before. And as a result of that, you have a lot of confidence on your, at least the numerical resolution, right? And we can also make it much easier to compare different turbulence models, different levels of physical fidelity. So all of this just makes it, removes the barriers towards engineers having to trade off between getting to the solution in a reasonable amount of time with reasonable cost versus having to potentially live with suboptimal decisions because of these constraints. Maybe John can also chime in into this question.
Well, I'll tell you, Chi-Chi, while you were going through that, I was kind of thinking back on the solutions that we did show. And I do want to point out that the cases that we are showing are extreme cases. It's it's mainly, if we showed the in-flight conditions, it'd be boring. There'd be none of this turbulence and stuff going on. For example, on the propulsion airframe, well, the ingested vortex of the other video.
Yeah, this one.
That is we're sitting on the ground, 0 speed forward, waiting to take off on our takeoff roll, and we have a large crosswind coming directly 90 degrees from the side of the airplane. Even at these conditions, once we start rolling, well, first off, I've mitigated the vortex ingestion, but once we start rolling, we shed that ingestion into the engine before we rotate. When we rotate, this engine is at full max takeoff thrust. It's drawing as much air into the inlet as possible. And we are working the propulsion airframe integration in such a manner that even at that rotation point, it is the most difficult point on keeping the aircraft's boundary layer out of the inlet. But we're working to, at that point, keep the distortion at the fan basically 0 distortion. In fact, we're able to get to points where the distortion at the fan face or the aerodynamic interface plane are less than what a conventional airplane that just does an over rotation with an engine hanging out in front of the wing under the wing. So now that isn't so much because of we're better designers. It's just that the situation with this installation is different. And the airframe itself actually is a big turning vane. So that inlet sees basically the same condition, whether we're at 2 degrees angle of attack or 10. And whether we're at 2/10 Mach number or basically cruise. So the conditions of the engine are a little bit different, but in some sense, that is an easier problem than on a conventional aircraft. What we're doing here with this semi-buried engine makes it very difficult. It's as difficult as some of the aircraft out there that have a very close coupled engine to wing installations. This is very similar in that respect. But we have the confidence with the CFD, the methods that we're using, the rigor that we put into the mesh quality, the rigor that we put into mesh sensitivity studies. And, you know, a lot of this is stuff that we've been trying to teach through the drag prediction workshop series and high lift prediction workshop series at AIAA over the, you know, I was part of starting that in the year 2000. So here we are at 2025, 25 years later, we're still learning, but we have a wealth of information and understanding and experience on how to deal with these very tough problems and be able to tame them with innovation and intellectual property that's unique to this airplane over the others.
Yeah, and our GPU-native code and also our workflow is applying this kind of a rigor, mesh convergence studies, validation and verification much easier than before.
Excellent. So, Chi-Chi, what's the benefit of GPU technology and advantages of hardware cost?
Oh yeah, we actually started our GPU code almost 10 years ago, exactly because we figured out back then that using GPU on industry standard flow simulations, unstructured flow simulations, is not just faster, but also cheaper. Because all the previous literature we saw was that it can be faster, but it was not clear it's going to be cheaper. And that was something we figured out 10 years ago that really made us jump into the wagon of we're developing a GPU native code from scratch. That's going to be much, much better, not just in terms of speed and scalability, but also in terms of cost. So right now, today we stand at a position that our GPU native code has a cost that's actually much lower than what traditional. Even if you take a free software like Fun3D and run it on your own cluster, the cost you're going to be having is going to be more than using our software.
We have a very highly engaged audience today. We're up to 83 questions. I know we won't be able to cover all of those today, but what we'll ask of Chi-Chi and John is to work with us to answer a majority of these questions, even if it's offline, and then we'll be able to provide some responses back to the audience. So then the follow-up question for you, Chi-Chi, on GPU and CFD is, what role does CFD play in aircraft design, especially unconventional ones?
Yeah, I think I was trying to answer that question in my presentation, but I think John probably has better answer than I do. Really, in unconventional airplane designs, just like what John had said on the location of the engines, it has enormous advantages, but also it has questions that you need to answer. That's basically different from conventional ones, right? So running a lot of simulations answers these questions, and for any potential problem you identify, you can also quickly iterate through potential solutions to these problems much faster than before.
Excellent. Okay, John and Chi-Chi, what is the role of low order methods, structured mesh CFD, multi-block structured mesh, and unstructured mesh CFD in modern aircraft design?
Well, I guess maybe I should field that one or try to. We use all of the above at JetZero. Low fidelity is very good for looking at your low speed stability calculations. It's very fast. These things run on PCs like nobody's business. We can look at large sets of data, even control surface deflections, and get pretty good handle on. We plugged the lower methods into our conceptual methods suite. So when we're doing basic sizing and studies, we're using lower order methods like they're just another empirical method almost. But it's physics-based, and instead of being a fit through data that we've collected historically, we're just analyzing the aircraft. So that's the real strength of using lower order methods and the way we're implementing it here at JetZero. It's embedded right into the conceptual methods. On the other end of the spectrum, we've been using RANs and structured mesh. Our structured mesh capabilities include multi-block, which you brought up, overset, and we can deal with fairly complex geometries. And it's the methods that we're using in that world for the past several years are really, we're using them for the aircraft design, the OML, the outer mold line, I should say, design of the aircraft and the propulsion airframe integration. But when we start to get to more complex configurations that include gear wells, landing gear out, gear doors, and you name it, it's so labor intensive to get multi-block, especially grid set up about those kind of configurations. So that's where we step into unstructured mesh. And now with this collaboration with Flexcompute, we'll be able to look at even the easiest of our complex geometries in a rapid grid generation, less labor intensive manner, but also extend that to studying acoustic problems. The BWB, one thing about that platform is that with our engines installed above, we have this great opportunity to really reduce the community noise. And I believe that right now, even with the engines on our demonstrator, we're running at about 27 dBs below stage 5, which is just unheard of. And that's with 40 some odd year old engine technology. So, but at some point, other noise sources begin to creep in and overtake, and gear is a big source of that. And so we're really looking forward to looking at some of these problems when we have the time, using Flexcompute and the efficiencies of running on GPU hardware, so that we can beat the problem to death with grid resolution if we have to, and higher order methods, higher order schemes within Flow 360. Okay.
Outstanding. Again, there are a lot of questions here. Many are related to the graphics that you're using to illustrate. And so, Chi-Chi, can you speak to, how those tools work, and a little bit of background on those?
Okay, so the tools work really on a web environment. So you run CFD as if you are just running CFD using your laptop, right? So that is our cloud offering. And we have an on-prem equivalent, except for basically the web server, etc., is hosted on your company computer itself. So you submit the job on your laptop, and we have a web API or a Python API for you to automate your workflow. And the simulation is run on our cluster or your company's cluster if it's an on-prem deployment. The result is rendered directly on the web browser. So once the simulation is done, you can visualize the result in the browser itself. So the simulations, the graphics I was showing, maybe let me share my screen again, is essentially an isosurface that's generated within Flow 360 of the Q criterion. So basically the Q criterion is a scalar that we use to visualize vortices colored by the local Mach number.
Excellent. One of the audience also asked, have you looked at quantum computing to enhance your simulation models?
Not yet. We are keeping an eye on that, but there is it's not something we are currently actively investigating for CFD right now.
Thank you. So let's talk a little bit about net zero. So everyone is talking about net zero by 2050, but let's be real. Is humanity actually moving the needle, or just greenwashing with prettier designs?
Well, I won't speak for the industry, but at JetZero, we're moving the needle even just by reducing the fuel burn. Significant fuel burn benefits, whether you're looking at it at seat mile economics or trip mile economics. So that's kind of the first step in our plan. We're also looking to the future for hydrogen. We're doing studies with NASA and University of Illinois. There's an ACES project that's an ongoing activity, working to compare a Jet A class airplane with a liquid hydrogen, and looking for opportunities there. I'll just say that right now we're kind of in a catch-22. And when I say we, I don't mean JetZero, I mean the industry. It's like, well, the infrastructure isn't there, therefore we're not going to build an airplane. And because there's not an airplane that requires liquid hydrogen, the infrastructure isn't going to get built either. So we have to break that equation. And at JetZero, we are looking at ways to break that equation so that you don't have to have 1,000 airports that have liquid hydrogen at every airport. We just need to build an airplane that has long enough range with hydrogen so that you have just a handful of hydrogen hubs, and you can still cover a very large fraction of the city pairs within the domestic United States or continental United States.
Yeah, and the GPU technology also help reduce emission. Really, like when you look at GPUs, yes, if you look at the individual nodes, they consume a lot more power than the CPU nodes. But to run the same calculation, they are just so much faster that the amount of energy consumption of individual CFD simulations is a lot lower than the equivalent for CPUs. That is also the contributing factor of why it is actually cheaper to run CFD on GPUs than CPUs.
Excellent. So we have about 9 minutes left, and I have a few more questions here for both of you. So let me ask one question of each of you, and then we'll wrap up with some audience questions if that's acceptable.
Yeah.
Okay. Chi-Chi, how do you protect against the risk of CFD-driven design becoming a black box?
Okay. So by black box, you mean people don't understand what is going on inside?
Well, perhaps that, or just commoditized, perhaps.
Well, I mean, CFD is actually quite different from the machine learning stuff going on today, in that we are actually solving first the principle physics equations, right? I mean, like for those who don't is new to CFD, so the equations we are solving are really back into Isaac Newton's time: conservation of mass, conservation of momentum, conservation of energy, right? So there is nothing really magical or mysterious about the result of CFD. I mean, the only empirical model we have is a turbulence model, and I do hope machine learning is going to help us a lot on that. But pretty much most of CFD is really grounded on first principle physics. People look at a CFD solution, and you can reason about whether something you see is numerics or is physical by doing refinement studies. That's why like having a really fast cheap CFD code is good, because you can do grid refinement studies very fast, and you can also compare different turbulence models really fast. And I do see in the future we should actually have a multi-physics and multi-fidelity type of a framework built in, so that you can actually evaluate also different fidelities, just like what John said about low order models. So all of these is going to, I don't think a CFD is going to become a black box anytime soon.
Understood. If design decisions are increasingly data and AI driven, where's the line between automation and accountability?
What's the line between automation and what? Sorry.
I'm sorry. If design decisions are increasingly data and AI driven, where's the line between automation and accountability?
I'm not sure if that was a question for me, but I'll try to answer it. So accountability comes right down to the company and the people, working the problems. There is no world, the way I see it, where AI is going to take that responsibility. Artificial intelligence doesn't generate knowledge from nowhere or from the ether. It has to be fed a large database of information. What AI does help with is go through a large database and make connections that are difficult to make. Patterns that we as humans will see a lot of patterns inside a database, but we may miss a few just because the database is so large. AI can help us identify some of these patterns or trends that have been kind of camouflaged from us over the years, but it doesn't just produce knowledge without having information. And the databases are the same databases that Chi-Chi and I have been talking about. Something's going to have to feed that database, and that source of fuel that feeds that database are the CFD numerical simulations, as well as the creativity of the designers and developers of the aircraft that we're running the CFD on. But with that, I will say there's a place for AI, and it is to help us look for trends that we may be missing that we could capitalize on. It'll find trends that we're missing, but does us no good. We can't capitalize on it. So, that happens to humans all the time also. It's just that we don't make a big deal out of those. We just discard it and go on until we find a trend that makes sense. And then we highlight it and move forward. So I'm not sure if I'm addressing the question, but as far as the accountability is concerned, it's going to come right down to humans.
Thank you. So I have one question for you that is really from me here at AIAA, and in support of our Flexcompute AIAA corporate member. John, what made the difference, or what was the aha moment when you decided to move forward with Flexcompute's capabilities?
Well, I'll tell you what, I touched on this a little bit in my intro, but the thing that really attracted me to Flexcompute is I've known Chi-Chi for over 20 years, way back when he was working his PhD at Stanford. I've known a lot of the people that are on the Flexcompute team. They're the best in the business. I know that there's still a lot of things that they are working on to further develop Flow 360. That's great. It's great to know that they're going to continue developing capability into a CFD method. But they have a very rigorous method. It's very cost effective because of the fact that they've mapped it to a hardware that is, in terms of price performance, is very cost effective. And so, some of when you're switching architectures, computer architectures, you do have to sometimes really switch algorithmic mapping to the architectures to really squeeze out that performance and capitalize on that capability. It's great that there's potential there, but until you actually figure out a way to harness that potential, it's just a theory, right? But they've turned this corner. It's not just Flexcompute. The industry is starting to turn this corner, but Flexcompute is right there, running at the forefront of this technology, and they're helping define that state of the art as they move forward. Collaborating with Chi-Chi will just be fun for me. Okay, let me be honest with you, and it'll allow me to dabble with feeding ideas back to the development team there, including Philippe and Mike Park, who I also know quite well, and just seeing where we can go. Both Flexcompute and JetZero are startups. We have the same kind of mentality, in terms of we have to survive by being good, not by resting on our laurels, because we have none. We have to develop this capability that the whole world wants to get, and we understand that. Chi-Chi and Vera understand that, and so this is a very good fit from my perspective between the two companies.
Yeah, thank you. And I want to add that partners like John really help us also push our technology forward, right? So we are already one of the most robust CFD solvers in the industry, and just because of people like John, whenever we find any problems, we can actually dive right into the numerical schemes. And just like what John said, because we have to engineer everything in the new. So we have the capability of looking at the potential problem or a problem we discovered in our collaboration and work out solutions in our CFD code themselves. So thanks for your support, John.
Well, that's
Yes.
wonderful. Sounds like two really incredibly brilliant teams who are leveraging your cumulative intelligence to solve these real world problems. And so congratulations on that. I want to thank you both for being here today, and to our audience. We really enjoy seeing sort of the authenticity that you can bring to these conversations, and to be able to share it out with our audience. And like we want to say at AIAA, we applaud companies like Flexcompute and JetZero who are breaking barriers. So congratulations. Thanks for being with us.
Thank you, Vicki. I do want to just shout out to both you and Amelia. You guys have supported us extremely well. This went off without a hitch in spite of dealing with folks like me. So thank you.
You've been great to work with. Thank you. My pleasure. Have a great day.
Thank you.
Thank you. Also, thank you.
Bye-bye.
Bye.